Okay, right. So this little talk is about. It follows on. Phil's talk about HNTAS into actual application of quality assurance practices on heat networks. So why do we need quality assurance on a heat network? That's an HRU installation. How to size, how to bind. That's an HNTAS job. That's a commercial installation. Is it possible to create effective quality assurance measures for heat networks without introducing a need to 100% external inspection and a workforce trained to perform those inspections? The asking here is it possible to, how far can we get quality control wise before we need to call in inspectors so that there's a minimal level of inspections required? So what do we know that works? A single KPI, when on public display, motivates all stakeholders to improve their own quality. The example of that is, we'll take the data HRU. So this is the first round of BESA results, as we touched on earlier, with a 15.8% degree VAR. So the BESA tests, this is a statement from Martin Crane, the author of the BESA regime. The testing clearly shows performance differences between substations. The simplicity of the VART as a benchmark of substation performance is having an impact, with manufacturers starting to publicise the VAR figure. Most manufacturers have made or brought forward planned substation improvements as a result of the testing. So this basically sums up that following the tests, they went on public display, and then all manufacturers were in exhibitions trying to publish their results, getting told to take their signs down because they weren't publishing the complete results. Very quickly became very apparent to all manufacturers in the industry that they had to get their house in order because the battleground was now on a VART figure. And it overnight transformed the industry. We're now, a number of years later, HRUs are good quality, and we can see how they work. So we know this works. You put a metric out there publicly, people improve their own quality. Certainly with house builders, if you can imagine, people building houses, heat networks, this is just as important to them. They don't want to have their figure out there in the public. How do we shine a light on poor efficiency in heat networks? So how do we see it? Okay, so this isn't how you do it. This is another slide of how not to do things. So how can we be sure that the systems we have in place on site to see things are actually themselves reliable? So we get this from the HNTAS KPIs. So one thing Phil touched on was a raft of KPI measures that have been used, the actual maths KPIs that are used to say yes or no, it works, it doesn't work, it complies, it doesn't comply, or yes or no, you cannot legally connect. Do the lights work? So data points, connectivity. This first one is for example, how do we know the visibility systems are working? So HNTAS calls for KPIs on number of devices reporting within certain time periods, number of points that are operational within expected ranges, the number of arms data points that are connected. So these are HNTAS KPIs. There's some others here, which some are HNTAS, some are others. But they give the idea. So you've got VART temperatures. On the other side, we have differential pressure temperatures. We have return temperatures from the network and the boilers. So these are the key metrics, top-line metrics for a heat network. If these are all green, then everything is efficient, and we've ticked all these HNTAS boxes. Okay, so I'm going to go through a load of KPIs now. So what we've been doing for the last year is effectively implementing these in real life situations. So all of these KPIs I'm showing you are coming off live sites. We'll start with substations. I'm not going to go into every box in detail, but this is a site, for example, with 4 substations on. again, everything green. This comes out of the BMS system, and this highlights to us, for example, this substation's working well. The second plate is maybe not as efficient as the first, and over on the other ones, there's some things that need investigating. And as we showed you before, your sensor thing. So these are just some KPIs that will give us the performance of substations and allow to direct tomorrow's works, so that by the end of the week the thing is green all over and complies. Oops, I got on me. Energy and bypass KPIs. So this is quite a big one. This comes out of getting your metering infrastructure in place. So where's all the energy go? What are your losses? What's your electrical consumption? So these come out of your BMS systems now. Primary network losses and bypass flow. Being able to put figures on it helps us identify things like the main bypass valve was leaking and letting by. But you get a figure now. You can go and change it. You can see the figure change, and you're actually fixing things. Gas boiler KPIs. Fuel conversion efficiency. This can vary wildly, how the boiler is actually set up, regardless of what the network's doing. This is live gas consumption KPIs from a site with 4 boilers, where the efficiency notably changes as you rotate between boilers. So this kind of dashboard actually tells the operator of the site, it gives them the information. They go, why is boiler 2 running twice as efficiently as boiler 1? Heat pump KPIs. So these came out of a job we did with Swansea, which was the world's first CO2 heat pump driven heat network. We were optimising the performance of CO2, which works better on nice high flow temperatures and nice low return temperatures. So these are the VART temperatures for a day's operation. 82 degrees average flow, 23 degrees average return, which is unheard of low. I know 23 degrees for a VART temperature is very low, but I'll show you why. Buffer store KPIs. What we were quite keen to do was to put a single metric on how well your buffer starges and loading and discharges, because it's quite a complex thing. You'll look at graphs and work it out. You can actually just put the sensor data through a fairly standard function, and it will give you the KPIs to allow us to spot when buffer stores are charging and discharging. If something goes wrong with sensors, controls, pumps, valves, and it stops loading and discharging, then they will go red, and you can attend to them. Central heating KPIs. So this is the fundamental reason why we got down to 23 degree VART temperatures now on some networks. It's to do with central heating. So this is manifold driven central heating in commercial buildings, where we've been able to work to actually control actuators. So you've got room CO2, actuator demand, room return temperatures and room temperatures. We're controlling these rooms here to typically about 20 degrees C. This form of fine level control allows us to get to the return temperatures. Again, it's KPIs. This room here wasn't working, the radiator's gone down, it's blue. It's visible alarms. This is the return temperature KPIs for that same site. So you see here all the different zones and the return temperatures. There are 2 sides to this site. One site was fitted with radiators and one site was fitting with fan convectors. The site with radiators, we were able to achieve room temperatures with much lower return temperatures, much stable return temperatures than fan cool systems. The fan cool systems are bringing us alarms up of high return temperatures after this day's operation. Because the radiators, the average VAR is very low. It's about 16 degrees, 17. It's actually below room temperature of a set point because there's a gradient of air in the room. It's that tight. Okay, water quality. So this is a Heatweb unit, the Aquila 2, simply connected up through the BMS MQTT. So you've got eyes on your key KPIs, conductivity, crevice corrosion, oxygen content. So anything goes off-piste or goes wrong, this will highlight it to you. It doesn't replace, obviously, maintenance and keeping things on site, but you can also check sensor accuracy, and there are things you can do for that. Net zero KPIs, where we're trying to get to net zero, we're trying to save energy, and that benchmarking I told you about earlier is quite a key KPI now in the journey towards net zero. So how do we do all of this? That's a lot of KPIs. It's a lot of work to be done. The nice thing is once you've done it once, you never have to really do it again. You just have to load it onto a system. What we're talking about is BMS-based quality assurance. So every site has a BMS panel, a lovely big machine that should run the site efficiently, and its job is to tell you when it's going wrong. So there is your £50,000 quality assessor that you've already paid for on site. We just need to make use of it, better use of it. So we break out the data points from your BMS system. So here is a site in London. It's one page, you can see there's a bunch of broken out 15 pages of data points. Energy centre, boiler 3, driver, enable. Low temperature hot water system, sensor, differential pressure. So these are data points in BMS. Everything in the BMS, all the boiler points, all the VART temperatures, all the sensors, everything is in the BMS. If you label it correctly, which is about a day's work, you have this at your disposal. The entire operation of the entire heat network, top to bottom, as transparent as a piece of glass. So we use the MQTT functions which are already built into the BMS systems. So they're there already and they're used by BMS engineers who know their stuff to talk between sites to swap data. What we do is we use exactly the same system. So here we have various controllers, meters and all that stuff. They've got MQTT functionality built in, we've turned it on. So now we're sending this data up to an MQTT server. In this, for example, we've got differential pressure sensor data. So we were firing it up from a site, for example, that was a couple of miles away, through the cloud, back into the plant room. So this is the infrastructure that BMS engineers use to move data around. We are using exactly the same system without introducing anything new to provide quality control. The extra layer, so MQTT is about transporting data, it's moving it around, it doesn't really store it. So on top of this you need a database, time series database that stores. So there's your traffic going around with all your sensors data, and it goes, it fires, it disappears. You bring it into a database, so you store it in time series data. You've also got charts of like some access rules, who gets access to what data, your point definitions, what is a flow temperature, what's its units, what's its maximum, minimum, what's its description. And your KPI functions. What is a VART temperature? How do you work out a VART temperature given a flow and a flow rate? How do you create these red boxes and orange boxes? So they are KPI functions that reside in the database, and they're loaded up once to start with. They give you something like this. So this is SQL based on standard query language. So PostgreSQL database, the one we use, is the most popular database in the world by a long way now. It's used by Microsoft, Google, you name it. Instagram, everyone uses PostgreSQL database. Within there we can create our functions. So function weighted average. How do you calculate the volume weighted return temperature? You pop it into this function, you tell it I want to know that for my site, I want the site-wide heat meter return temperature and I want it weighted on the flow rate. And this is what you'll get out the other end. So you just literally type that in as your function and the software will give you this out. So this is now open source. Anyone can go home and start using this stuff tonight. No charge, never will be a charge. All you need to know is the function that creates a function where volume weighted average. So we've not been invited to be part of the HNTAS trials in any way. So we've run our own in parallel in partnership with Vistry Homes, which is Canning Town High Street. It's 1,000 properties, a Premier Inn, some commercial shops. So it's a nice big site, 7 substations, proper site, everything's there that can go wrong. Here we have the main one of the dashboard. There are quite a few dashboards, but this is the headline dashboard that we're using for optimizing. We've got some high return temperatures. The secondary sides are not great. The buffer stores now, we've replumbed them, they're working well. we're getting on top of things. The efficiencies have come down about 20% on this site over the last year. So that's tracked improvements. Just on the primary side, we haven't tacked the secondary. So this is plant room optimization, can save you up to 15-20% just on gas boiler efficiency. The same system gives us operational alerts, so the engineers get phone calls if they want when the boilers go down, and those will go through various rules. So this is your automatic quality control system. It's integral. And again, this is all open source. It's loaded up. Once it's set up, it's up to you how you want to manage it. But basically, you have a system here where you can link any data point in your BMS through to an alarm and direct that to the appropriate engineers. There's organisation and user management. So big thing about these systems is you're trying to share data. You're trying to get everyone's quality control up to speed. And that may mean you may have a Barclays site with a main contractor, a metering company, the organisations, and they're all going to want to access this data, and some of them aren't going to be allowed to see some of it, some of them you want to see others. The nice thing about open source software at this level is it's got organisation built in. So if you're running a site, you can create an organisation, which is effectively just a grouping. It may be a site, it may be, this is the contractor's organisation, and on there you put your dashboards and your KPIs that engineering team uses. So it's under your control. Who gets to see what, how, when? How is this achieved? This is achieved by using 3 of the world's most popular open source programs. So MQTT, as we talked about, for data transport. Postgre, the world's most popular open source database, and Grafana, which is used by everyone, Microsoft, Google, for visualization. So these tools put together give you possibly the best quality assurance system for heat networks you could ask for. It's all open source. It can be managed for you, taken in-house, run free of charge. There's never any risk, and it can be shared around. So that's the beauty of open source. This is why people like the Department of Defence use open source software. To make this all possible, we have created a GitHub site. So this is really the output from our government-funded SBRI project. So we were funded to create open source control systems for the heat network industry. And part of it was to set up collaborative, so everyone could collaborate. And out of that has come a GitHub site where all of the KPIs, all the software we're talking about is available. The commissioning software is available. If you go to Heatweb, HNQAP, which stands for Heat Network Quality Assurance Procedures, publication, sorry. It's a mirror. I used to work for the Ministry of Defence in the quality assurance. So this is a mirror of AQAP, Allied Quality Assurance Procedures, which is the procedural documentation used between NATO allies to make sure all the different militaries' quality assurance gels. So we've effectively replicated that system, that way of doing things, procedural guidance. We've open sourced it, and we put all this software that we've talked about, all the KPIs there. So this is available for everyone to use now, to install into their BMS panels and to get those KPIs. Right, I'll finish on a couple of slides. Right, what does the governor say? This is Mark Carney, the ex-governor of the Bank of England. So on some measures we have 10 years left before we've blown through the 1.5 degree carbon target. So time is ticking. We all know what gets measured gets managed. Climate change is not yet consistently measured, although the private sector has moved in this direction. We now need to make measurement and disclosure mandatory. And my last slide is how we think the government could help get this kind of quality assurance procedure up and going quite quickly. So that would be to set a deadline for all panels in all plant rooms everywhere, because they've all got them. There's a deadline to get that function turned on within 2 years and connect that data to Ofgem. So Ofgem are connected to every one of these main energy centre plant rooms and getting the KPIs, the HNTAS KPIs, automatically that they're after. 2 years, and that process is automated. Provide grants. Obviously, some head ends of systems are going to be old and ancient, so the excuse, it's not up to it. Okay, so here's 5,000 grand. Get the BMS system fully up to date, the head ends in scratch, talking to Ofgem, and in the process, the whole site will obviously should be working. They'll have visibility, no excuses for it not to work. So that's That's you know, a quarter of what you'd spend on an H&S job, and you'll probably get a lot more out of it. And the last thing is to make open source collaboration a centrepiece of quality control. The number of technical things we've got to fault find here is vast. It's going to take specialist gas engineers, specialist heat pump engineers to decide these KPIs. That's going to take collaboration, open collaboration. And there's people don't want to give their secrets up to us, so we need to get together. So we're quite keen to make collaboration a centrepiece of this quality assurance going forwards. Okay, thank you very much.